Hi, in this video, I'm going to explain how to use Uncertainty-Penalized Bayesian information criterion for parametric PDE discovery. I am Pongpisit from Osaka University. This work is all about data-driven discovery. Let's say you're given spatio-temporal data, which varies in space and time. The goal here is to discover the unknown governing equation without much prior knowledge. This is very different from deriving physics from first principles, where you essentially use mathematical deduction to obtain new knowledge. Note that in this presentation, I mainly use the Burgert's PDE as an example. Mathematically speaking, we can identify the governing equation by solving a system of linear equations. We can gather a lot of candidate terms into a library and then solve for a sparse vector of PDE coefficients. Because we usually assume that dynamical systems are often governed by just a few dominant variables. So here, we have the L0 norm optimization problem to tackle to prevent the possibility that discovery results are sensitive to this regularization hyperparameter lambda, meaning that we may get results that are just too sparse, overly complicated, or sometimes miss the true governing form. So we will solve for the sparse vector of coefficients via an application of best subset selection and an information criterion instead. Best subset selection lets you achieve the optimal solution with a specific number of active terms or the support sites, which you can totally control. So our plan is to solve the best subsets with different number of non-zero terms, calculate an information criterion for each subset, then finally hopefully we can select the best one. Information criteria balance model accuracy and model complexity. The most famous criterion are AIC and BIC, which differ in how much penalty is applied to a model for its complexity. As you can see on the right-hand side figure here, BIC is more conservative, penalizing complexity more heavily than AIC. However, in this context, in this example in particular, both of them tend to prefer overfitted PDEs. Then our research, in fact, introduces a new information criterion to address this issue of overfitting in model selection. Here we propose a new criterion called UBIC that using BIC as the base penalizes a model more for its PDE uncertainty. The intuition is that the governing equation should achieve a good fit with just a few dominant terms that are also stable. Less uncertainty. If you can recall the system of linear equations we discussed earlier, you can always quantify the uncertainty of the vector PDE coefficients using many techniques from Bayesian learning, or more particularly in our research, we use Bayesian linear regression to quantify the uncertainty of the coefficient vector. That actually represents the PDE. The PDE uncertainty here is proportional to the sum of every posterior standard deviation, considering just active terms divided by the L1 norm here, divided by the L1 norm of the posterior mean of the coefficient vector. We use V as the posterior covariance matrix. Using the same example, you can now see that the PDE uncertainty is a useful piece of information that can signify the true support site. And consequently, our UBIC successfully selects the governing equation. In our workshop paper, we do consider a more challenging problem of parametric PDE discovery. Specifically, we ask what if the PDE coefficients are not constants, but varying functions of either space or time. This is exemplified by the time-dependent Burgert equation. The solution to this new scenario is actually quite straightforward. One can solve for the best subset and compute the PDE uncertainty for each time step. And our new contribution is that we propose the extended UBIC, which builds upon the accumulation of every quantified PDE uncertainty. And we would like to conclude our presentation with this numerical result section. First, on the left-hand side, it is quite evident that the corrected AIC often selects overfitted PDEs. This issue can be addressed by leveraging insight provided by quantified PDE uncertainty. Furthermore, as you can see, our UBIC consistently identifies the true governing equation. In the rightmost subfigure, we demonstrate that the quantified PDE uncertainty can construct a confident interval for an estimated coefficient at a specific point in time or space. That's all.